Greetings, Internet, and hello, my scientific comrades. I'd like to welcome you to my very first video in the channel, which I started as a means to share some of my knowledge with the world. If there is one thing which I have in this life, apart from an undying passion for science and philosophy, is an innate desire to understand more about the universe. And so, by making this channel, I hope to be of help to those who, like me, have an insatiable thirst for knowledge. In this first video of mine, as the title would suggest, I shall attempt to enlighten you, dear viewer, that is, if you don't know already, about a fundamental part about not just physics, but math and other sciences out there. Prefixes for units, and the units themselves. So without further ado, let's get started with some foundations for you to have in order to better understand some of the more interesting stuff coming up in later videos. Hopefully. If this channel doesn't die before then, that is. Chapter 1. Units. So units, in case you don't know, are defined as an established reference used to define the magnitude of a quantity. In other words, they tell us how much of a given thing there is. For example, the unit for length is meters, and so whenever we want to, for instance, say how tall we are really just trying to say what our vertical length is. But how could we say what our vertical length is? And well, the way in which we usually do this is by saying how much our vertical length is in relation to other things. So for example, one could say that they are 8 twigs of equal length tall. And so that way one can convey to others an accurate picture of their height, in theory. The problem with that statement is that 1, twigs vary in length, and so depending on the length of each twig, even if the length of all of them is equal, that statement would carry very different meanings depending on who you're talking to, as the very nature of the statement is open to interpretation, given us how there is no one universal length for a twig. And 2, things aren't generally straight, which can then convey, once again, a different image of the statement to whoever you're talking to, since different people might interpret it taking into account the full length of the twig, or the height of it. And so, in light of this new insight, I'm sure you can now see why we need a proper unit of measurement, which is objective and does not vary depending on who you ask. Enter the metric system. Unless you're American, in which case then the imperial system is the one you have to worry about. But we'll get to that in just a minute. Whatever the case, the metric system is the one which is universally used, and so we'll just stick to that one for now. The metric system, as I'm sure you know, is an objective system of units in which the base unit, the meter, is the same regardless of where in the universe you are. So a meter is the same in America, as in Asia, as in the Moon, as in Jupiter, as in Gaia BH1, as in Alpha Centauri, as in Sagittarius A, as in the Andromeda Galaxy, as in the cosmic microwave background radiation. You get the idea. So great, we know how a meter works. But just how long is a meter? In order to have an objective unit of measurement, we have to define what the unit of measurement is, after all. So, what exactly do we mean when we say things like, oh yeah, my height is 180, or 163, or 190, or so on? And well, back in the olden days, a meter used to be defined as 1/10,000,000th of a line running through Paris from the equator to the North Pole. And so a meter, it was agreed, would really just be a digestible fraction of a distance with which we could measure different things. And that's how we started to measure length. But of course, the ways in which we define units now have changed to much more objective means, relative to other constants in the universe as opposed to things which are susceptible to change. As an example, why don't we continue using the unit of length, the meter? As we already discussed, it used to be measured relative to 1/10,000,000th of a line running through Paris from the North Pole to the equator. But nowadays, a meter is defined as the distance which light travels in 1/299,792,458th of a second. A fitting definition, seeing as how the speed of light is 299,792,458 meters per second, which, as we'll discuss in a later part of this video, really just means that every second that passes, light travels 299,792,458 meters. Or in other words, pretty flippin' fast. Going on a side tangent though, despite its criticisms, the imperial system works just as well as the metric one because its foundation is the same, as it's also, much like the metric system, an objective system of measurement with which we can measure length. The only real reason as to why the metric system is so much more highly regarded as opposed to the empirical one is that the metric system is pretty much used in the entire world, whereas the imperial system is really only used by the freedom fighters in the land of the free and the home of the brave. So that's the basis of how we come to define units of measurement. But that's enough of units of length. Let's focus on units for other readings, shall we? In the world of science, there are 7 fundamental units with which we measure things. Now, of course, there are more than 7 units, such as meters per second, newtons, joules, voltage, watts, etc. But beyond these units, there are 7 units with which we make up literally every single other unit in existence. And those units are part of the Système International des Units, or the International System of Units, otherwise known as the SI Units for short. In many ways, the Avengers of Science, a super duper ultra mega super exclusive club in which only the big boys can be in. This group consists of the following units: the meter, the unit of length; the second, the unit of time; Kelvin, the unit of temperature; the kilogram, the unit of mass; the ampere, the unit for electrical current; the mole, the unit for the amount of a substance; and last, but most certainly not least, the candela, the measure of luminous intensity. Although it should be important to know that we don't really deal with that last one outside of university physics, or, the IB diploma. These are the units with which we can measure pretty much everything in the universe, as every other unit out there is a combination of the previously mentioned. For instance, take speed. We can calculate speed using the formula v equals s over t, or in words, speed is equal to the distance divided by the time taken, where the lowercase t is the symbol for time, coming from, well, the word time, the letter s being the symbol for distance, coming from the Latin word spatium, which simply translates to space, as in the space between 2 points, otherwise known as displacement, or, simply put, distance. And finally, the letter v, being the symbol for both speed and velocity. This raises a question though. What's the difference between speed and velocity? And if there is a difference, why should they share the same formula? And well, they both exist to describe the same thing, how fast something is going. And so under this logic, they can both share the same formula because the same variables are needed in order to measure how fast something is going, those being the distance and the time. So that answers one of the questions, but one query still remains. How are they different then? The difference between speed and velocity lies in the direction in which the object being described is traveling. You see, in physics, there is something called scalar and vector quantities. Scalar quantities only have one property: they have a magnitude. And vector quantities have 3 requirements to be called a vector quantity: both magnitude, a direction, and a point of application. So in the case of speed and velocity, speed is a scalar quantity, whereas velocity is one of those vector quantities. This then means that velocity is really just the same as speed, but with an added distance factor. Here's an example. Say an object, a car, is moving in a circular path, and this car is going at a constant speed of 10 meters per second. That is to say, that it's not accelerating, nor is it decelerating. At every single point of the path, it's going at the same 10 meters per second. In order to describe the motion of this car, we can then say that it's moving at a constant speed, but its velocity is constantly changing, because it's constantly changing the direction in which it's going. And so, as can be seen in the formula v equals s over t, in order to get the speed of an object, we must take the distance which the object travels, measured in meters, and divide it by the time which the object takes to travel said distance, measured in seconds. And so when we divide meters by seconds, we get the unit for speed, being meters per second, which is just a way to say the meters traveled every second. So 10 meters per second is really just a way to express that an object is moving so fast, it's moving 10 meters every second that passes. Am I repeating myself too much? Now, meters per second is one of the many units which is derived from the units of the International System of Units. But as I've mentioned before, there are also a lot of others. Meters per second is really easily told apart because the unit is pretty much arranged in the same way as the units it's made up of. Take as another non-specific example, the unit of force, the Newton. We can calculate force using the formula F equals ma, or in words, the force is equal to the mass times the acceleration. Now, as we've already seen, mass is measured in kilograms. That's one part of the formula. And in case you don't know, acceleration is defined as the change in velocity, with the formula v minus u over t, with v being the velocity as we're done measuring, and u being the velocity as we begin to measure. Or simply put, u is the velocity before, and v is the velocity after, and these two subtract to give us one final value for the change in velocity, which has the unit of velocity, being meters per second. Once you take that value and divide it by time, which has the unit of seconds, you get meters per second every second. Or in other words, meters per second per second. An easier way to write that would be meters per second squared. So great, we got the unit for acceleration, meters per second squared. And with that, we can now complete the units used in the formula for force. And we can see that to get the force an object is exerting onto something, we have to get its mass, measured in kilograms, and its acceleration, measured in meters per second squared. So the unit of force then becomes kilogram meters per second squared. This unit, however, like many others, is a bit of a mouthful. And so in order to simplify this, we just make a new symbol, with a new name in order to represent this unit. And in the case of force, the unit that was made up to represent kilogram meters per second squared was the Newton, with the symbol N, named after none other than English mathematician, physicist, astronomer, alchemist, and theologian, Sir Isaac Newton. AKA the man who single-handedly developed the theory of gravity, a new theory of light and color, 3 whole freaking laws of motion, invented the first damn reflecting telescope, and is more often than not credited with inventing calculus. So, you might have heard of him at some point or another. And whether or not you consider him as the legitimate inventor of calculus, it is a fact that he did independently develop calculus even despite publishing this new discovery after Leibniz had already published his own paper on calculus in 1684. And perhaps, it should also be important to note that Newton called it method of fluxions, and not calculus. But I'm sidetracking now, and while I'm sure you loved that little tangent on Newton and the incredibly brief history of calculus, we gotta stay consistent and get back to units. I might make a video on calculus some other time though. But anyway, the last thing I like to mention about units is the prefixes which they use in order to express their quantity. So, for instance, once more using the metric system as an example, you might have heard other people throwing the word kilometer or millimeter out there in order to express very large or very small quantities. This is the very use of unit prefixes, to describe that which is smaller than the unit itself, or that which is abysmally larger than it. So to put this into perspective, kilo just means the value of the unit times 10 to the power of 3, or in other words, the unit with 3 zeros following behind it, which just means 1000 times the unit, as 1000 has 3 zeros following behind it. Think of them as instrumental backing for the main characters, the units. Amongst these prefixes, you may find the following: milli, to represent times 10 to the negative 3, micro, to represent times 10 to the negative 6, nano, to represent times 10 to the negative 9, pico, to represent times 10 to the negative 12, temo, to represent times 10 to the negative 15, and so on. Apart from these though, there are also the ones to convey larger versions of the units. So say, the previously discussed kilo, which represents times 10 to the 3, as previously mentioned, mega, to represent times 10 to the 6, or a million, giga, to represent times 10 to the 9, or a billion, and who could forget, tera, to represent times 10 to the 12, or a trillion of any given unit.